this is going to work. You'll be able to see me. Welcome back to chemistry. It is late on Sunday night. We had a wonderful thunderstorm. Lots and lots of rain in Rockwall. Not sure how much we got out here, but when I came home my internet's down. So I will just continue this lecture from where I think I stopped on the other one. First lame joke. Only lame joke for tonight, if I can remember it. What do you call the scuba diver who's afraid of the water? Well, he's the chicken of the sea. Let's go ahead and keep on working with Chapter 1, Module number 1. All this really is about, this whole first chapter, is working with units, converting between different systems of units, multiplying and dividing units. And it's when you multiply and divide units, add and subtract units together, that you begin working with what they call derived units. And something to remember is that if you're going to add and subtract units, the units have to be identical. And that's sort of directly taken from algebra, adding and subtracting units. They must be identical. And you know that because if you're going to add 2 boxes plus 2 boxes, you have 4 boxes altogether. If you're going to add 2 apples plus 2 apples, you're going to add 2x plus 2x, you get 4x. However, if you try to add 2 boxes plus 2 stars, can you combine those together? No, you can't. You end up with 2 boxes and 2 stars. Trying to add 2x plus 2y together, and you can't do that either. Because in order to add or subtract algebraic expressions, the variables have to be the same. In other words, you combine like items together. The way that you combine apples and oranges is you get fruit salad. You can't say that 2 apples plus 2 bananas is 2 bananas or something, or apples. They don't combine like that. You just have 2 apples, 2 bananas. So when you're adding or subtracting units, the units have to be identical. Makes sense to you. If you're going to measure how many pounds of something you have or how many ounces of candy, if you have 4 ounces of chocolate and 2 ounces of peppermint, and I asked you to tell me how much candy, how many ounces of candy you had all together, it would be very easy. You'd say, well, I've got 6 ounces of candy. It happens to be divided up that I have twice as much chocolate as peppermint. I have 4 ounces of chocolate as I do peppermint. But altogether, I have 6 ounces of candy. Now, let's say, instead of the candy being given to you in ounces, you had 1/2 pound of peanuts, and you had 6 ounces of cashews. And the question was, what's the total quantity of nuts that you have altogether? Well, can you say you have 6 1/2 pound ounces of nuts, or something equally strange? Well, no, of course not. You know that you either have to change the cashews quantity into ounces, or you convert the pounds into ounces. And since there's no reason to go through the conversion, you have 8 ounces of peanuts plus 6 ounces of cashews is 14 ounces of nuts in all. So when you're adding or subtracting units, it works just the same way as just with algebraic expressions. The units have to be identical. if you have grams in milligrams, you have to convert either the milligrams to the grams or the grams into milligrams. So adding and subtracting the units have to be the same. It's not the same way though with multiplying and dividing units. So first we are adding and subtracting units, then we are multiplying or dividing units. Multiplying, dividing units. Dividing. We have a different situation altogether when we're multiplying and dividing. You learn that if you had 5x times 5x, that's equal to 25x squared, because you learned that when you multiplied bases that were the same together, you added the exponent. So if you have x times x, that was x squared, or x times x times x, you had 3, the x used as a factor 3 times, so you had x cubed. But then what happened when you had 5x times 30y? If you'd been trying to add or subtract 5x and 30y, there would be nothing else that you would be able to do, because the only way that you can combine or take apart, any way that you can subtract units and algebraic expressions is if they're identical. But with multiplication, because our associative property of multiplication says that it doesn't matter what order we do our multiplication in, that a times b times c is the same as a times the quantity b times c. You can sort of change the order in here. So you have 5 times 30 times x times y, or you have 150 xy. When you're dividing or multiplying units, they work just the same way as variables do. So if you would have 12 feet times 3 pounds, you would multiply this just like an algebraic expression. 12 times 3 is 36 foot-pounds, which is really strange, but that's actually an English measure. I think it's force, I'm not sure. But foot-pounds is something that's actually used in science. So this is what you have to understand, that you do the same thing with units. Adding and subtracting, the units have to be identical. Multiplying and dividing, the units can remain just exactly as they are. Now see, I'll tell you right now that I'm working hard just like you are, taking chemistry, but it's been a long time ago. See here? Well, these are my notes that I'm taking. I have worked all of the problems that are in module number 1. See, there's more notes in here. If I'm taking multiple hours to work through the chemistry, it's very natural to expect you guys to take multiple hours and sit and study with somebody, sit and study with my videos if you need to, but work together and remember that the work that you're doing here is adult level education. This is just not middle school, elementary school. This is an authentic adult level class. So, continuing on with my class notes, we're talking about how we make measurements. And you'd think, Ms. Betsy, I've been measuring with a ruler for a really long time now. You surely don't need, surely you're not going to tell me how to measure with a ruler. Well, actually, yes I am. Okay? Let's say that I have this ruler here. And I'm going to actually attempt to make it there's 1, 2, 3, 4, 5, 6 inches. I'm going to split this into 3 and split this here. It's actually sort of evenly divided. And I'm just so glad that you guys give me a lot of slack here, cut me a lot of grace. Whoops, 10, 11, 12. And here's at the beginning, and they don't write 0, but this place right here is how we measure. Now, if you're actually going to go ahead and measure something with a ruler, what do most of us do? Well, we line up the end of that ruler with the thing that we're measuring. So here we would say that this book is just about 6 units long. But what happens, paper erases really well, look at that. What happens if we actually attempt to line the item that we're measuring up right here at the end of this ruler, it's not really exactly as good measurement as it can be because this might be worn here, you've used a lot, or it's fat, or how are you making sure that you get the end of that item right up against the end of the ruler. So when you're making scientific measurements, and actually when you're measuring just in general, it's much more accurate for you to begin at number 1 on your ruler. Or if you don't want to do number 1, pick number 3. It's just your arithmetic is easier. So if I begin at 1 and measure to 7, then 7 minus 1 gives me the measure of this as being 6 units. So the first thing that you want to do is begin measuring at 1, and with all of that, I turn my note pages over. Let me get back, because there's no way that I can teach this without notes. So first, when you're measuring, you're going to begin at 1, not at 0. Not 0. That will help you to come up with a better measurement. The second thing that you have to do is determine the scale. When we're talking about the scale, you might have we're going to pretend that this is inches. Okay, this is 12 inches. So how do they have each one of these inches divided? If it looks like this, well, sure, you recognize this. This is not a very, very precise measure, but you have 1, 2, 3 extra lines dividing this, which means it divides this 1-inch space into 4 equal distances. So this is measured in 1/4 inches. Now if we had an extra division in there, in between there, just sort of like this, the scale for this is to the nearest 1/8 of an inch. 1/8 inch. That is like really rotten writing. So you have to figure out what your scale is. It doesn't do you any good. It goes back to that units at the beginning. Make me curtains that are 50 by 60. 50 by 60 what? Okay, is this inches? Is this feet? Is it centimeters? Is it meters? Make sure that you know what your scale is. And then when you're measuring, you're going to want to estimate in between the dividing lines. Estimate in between the dashes. Estimate. I'm going to just say estimate to the next level. Very bad way to describe it. But let's say that this is a blown up piece of 1 inch and it is divided into quarters. Okay? 1/4 inch, 1/2 inch, 3/4 inch, 1 inch. We're going to say that this is 1 inch. And then it's further divided into 1/8. Blech. eighths. 1, 2, 3, 4, 5, 6, 7. 7 divisions is one less than the quantity than the number of spaces this is divided up into. Now let's say that we measure this piece of string or this piece of rope or whatever it is, and I probably better go ahead over here and say, you know, this is 1 and this is 0, because when we begin measuring, where are we going to begin measuring? Are we going to begin measuring at the end of the ruler? At the end of our measuring utensil? No. We're going to begin measuring at 1. So this thing is just going out here and it comes to right about there. So this whole quantity here, this whole dimension is 1 inch. We're calling it 1 inch. This is ½ an inch. This is 5/8 of an inch. But look at where the end of this thing comes. It comes down into here. So when you're measuring, you can actually estimate one level smaller than your scale is. Here we have 1/8, 2/8, 3/8, 4/8, 5/8. So in between here, it's more than a half, which is 4/8. It's less than 5/8. So it's somewhere between, okay, so 4/8 is equal to 8/16. 5/8 is equal to 10/16. 8/16, 10/16, this is maybe 9/16. So you're going to be able to estimate when you're measuring one level clearer than what is written out here for you. I hope you can understand what I'm saying. So what you're going to do is read the scale to the next plate. You estimate, and then you read the scale to the next decimal place. Decimal place. Now you remember when you first began Algebra 1, you had been working with fractions, and you would come up with this problem here, with this solution here. You would have 8/5. You would say, oh, 8/5 is not right. I have to make that into a mixed number, which is 1 3/5. And then you got into algebra, and I told you, or your algebra teacher said, no, this is actually better to leave it as an improper fraction reduced to lowest terms than it is to convert it to a mixed number, because this is going to be the way that we're going to work with that a lot in algebra. Well, what happens in the language of science, in the world of science, is they don't really like fractions a lot. It's much easier for them to work with decimal numbers, particularly because they work with scientific notation, which we'll talk about at the end of this chapter. So if you have a fraction, you want to go ahead and convert that into the decimal. I picked 1/8 because 0.125 is an easily learned decimal equivalent to 1/8 that you guys might not know off the top of your head. How do you figure out what 1/8 is if you don't know? Well, exactly what this says. 1 divided by 8. Punch it into your calculator. 1 divided by 8, and you get 0.125. So that's what you're going to do when you're measuring distance. Something that uses a measuring tape or a ruler or a meter stick or something like that. Well, what happens if you're measuring volume? And volume is liters, is the base unit in the metric system. Gallons is the base unit in the English system. And where you're going to measure that a lot in chemistry is you're going to have something that's called a graduated cylinder. And it's just exactly what it says. It's a cylindrical stand. You know, it's a cylinder here, skinny, sort of like a rain gauge that some people have in a garden. And it's called a graduated cylinder because it's marked off in a similar manner to how a thermometer is. So let's say that we have 10, 20, 30, 40, 50. And we're going to measure how much liquid there is in this cylinder. And we're going to use the cylinder frequently instead of a measuring cup. And I'm looking to see if I see another color marker out here, and I don't immediately see one. What you're going to find is that there is a force of attraction between a liquid and the side of this cylinder, this graduated cylinder. So when you pour a liquid into a graduated cylinder, and then and I say, okay, how much is in there? You can't just look, you don't look at it and you see a straight line. This is actually what it's going to look like. You know how you hold it up and look like this, you get down and you look at it. The liquid itself is actually sort of trying to climb up the sides of this glass cylinder. And you've got an arched shape. This line right here, the shape that that takes, that's called the meniscus. Meniscus. And all fluids that you measure in a graduated cylinder are going to do that because they're all going to tend to climb up the side of the cylinder, but they're not all going to climb up it evenly. So how in the world are you supposed to measure that? Look, the top of this has climbed clear up here to 40. But there's a pretty big difference between where it's climbed up the cylinder and where it is here in the middle. So when you are reading the level of a liquid, read at the bottom of the meniscus. Read at the bottom of the meniscus. Meniscus. So let's just say this is a milliliter graduated cylinder, 10 milliliters, 20, 30, 40 milliliters. And I said, okay, how many milliliters of liquid are in this graduated cylinder? You wouldn't say 40. It's not 40 milliliters. It's not 30. You know, you can easily go halfway. Maybe it's 35 millimeters. Maybe it's milliliters, 36, 37. But you know that you can get a lot closer than 40 milliliters. Maybe it's 35 milliliters. So when you read volumetric measurements, make sure that you read at the bottom of the meniscus. That's a crucial measuring rule for when you're going to be doing all of these scientific experiments. Remember, you want to measure to the next decimal place. I mean, this might even be 36 milliliters. But if you do 40, that's not nearly accurate enough. Now, I've talked about accuracy, and I've talked about precision. I've mentioned those two words. We have accuracy, and we have precision. And we have some pictures that I'm going to sketch for you. I really hope I wrote them. I guess I didn't. You can look in your book, and they have pictures of darts being shot on the bullseye. And what accuracy is how close a measure is to its value. How close a measurement is to its true value. And you have to have this note, measure meant is to its true value. Whoa. To its true value. And precision is, it's an indication of the scale on the measuring device that was used. Scale on the measuring device. These you just have to sit and think about for a bit. So, in other words, if with accuracy, this is sort of like a measure of how correct it is. The more correct it is, the more accurate it is. The more correct. Now for precision, the smaller the scale, the more precise. Precision, I can best illustrate when they talk about precision instruments, things that are precision. Precision instruments make fine, very fine differences of measurement and sculpting, and things are very smooth. In the world of construction, think of a circular saw as a saw that men and ladies, since I did it too, you hold in your hand, has a big blade on it, it's about this big blade, and you go, and you cut big pieces of wood in it, or you cut pieces of plywood. Or a huge sawmill that has this great big old honkin' saw blade on it that, maybe the blade is that, as thick as the end of my marker here. So it cuts off that big old chunk of material just when it cuts through, as opposed to what they call a scroll saw. I have a scroll saw, and the blade on it is as skinny as the needle on a sewing machine. So with my scroll saw blade, I can actually cut something that looks like that. Now if I tried to do that with a big old circular saw blade, I might be able to get that. Something like that. This is more precise. The scale on it's better. It's if you have a high quality measuring device that has all of these little hash marks on it. Maybe it measures it to the nearest centimeter, as opposed to a great big long measuring tape that measures to the nearest yard. Precision is the smaller the scale, the more precise it is. Accuracy is the closer to the target, the more correct the answer. That's what accuracy is. And they use pictures. You can be accurate but not precise. You can be precise but not accurate. And you can have both precision and accuracy. So if we had, this is our bullseye here, and here's our center bullseye that we're trying to get. Now if we have our holes all centered over here, this is precision. This is precise. Everything is close together. You have a nice tight shot pattern, but your, what's it called, that you look through. Your telescope is off, or your sighting is off. It's precise, but it's not accurate because you're trying to get this bullseye right here. And then let's say that you have this bullseye here, and here's the bullseye you're trying to get. And you've got this shot, and this shot. Here, let me make this bigger. Here's the bullseye, and here's one. Here's one. It's not real precise. They're all real, they're close, equally close to where you're headed, but it's not narrowed in real carefully. So this is accurate. You're getting pretty much close to it. But something that is both precise and accurate, you have your cluster is all just right there, it's together, and it's right at the target. And I'll be frank, I've always had a difficulty with accuracy and precision and with understanding them and using them. But basically, if you think of this, that the only way that you can get more precision, that's to get a better instrument. The finer the saw blade, the more precise the cut, the more specifically you can go. The finer the measuring instrument, the better your accuracy is. If I'm measuring yards of material by knowing that from the tip of my nose to the middle finger of my hand stretched out, that's about a yard. And that's how anybody who's ever done any purchasing of material or measuring of material, that's a good way to guesstimate. Okay, I've got 1, 2, 3, 4, 4.5 yards of material. Well, that's not really a very precise method. That's just a big guesstimate that tells you approximately how much you have. And then you get a yardstick, then you get a measuring tape, which is maybe closer. So precision has to do with the quality of the instrument. Accuracy has to do with how good a job you're doing. So if you do a sloppy job of, okay, measure this for me. In one time, you say you get 10.5 inches, and then the next time you get 11.5 inches, and then you get 10 inches, then you get 12 inches. That's not very accurate at all. You're just being sloppy. It has nothing to do with how good your instrument is. It just has to do with the accuracy of your work. Okay, I think I have beat that one to death. Significant figures. This is something that is very, very essential that you understand. Has to do with accuracy and precision and the scientific notation. And it's important because sometimes zeros are significant and sometimes they just sort of take up space, or they hold a place. So let's write down when a digit is significant. You need to write down these significant digits, significant figures, significant figures. Digits within a number are significant if they follow certain requirements, and we're going to see what these are. Significant. How do we know if a digit, it's this thing that holds us up that keeps grabbing my shirt. Digits within a number are significant if it's non-zero. I'm just going to say it's not zero. Any number except 0 is always significant, period, end of story. Okay, so if it's not 0, if it's 1, 2, 9, now these are just digits. What are our digits? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are digits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, they're automatically significant. Well then, there must be something special about zeros. So how do we determine if a 0 is significant or not? Okay, how else? Okay, it's 0, but it's between two non-zero digits. But it's between two significant digits. So if you have a string of zeros that are together in the middle of of a number, those are going to be significant, but you'll see why that is as time goes on. But for now, you have like 1, 0, 1. That 0 is significant because it's in between two digits that are significant simply because they're not 0. Okay. And this is the big condition here that you're going to have to worry about learning, or that is, I mean, it makes sense that if it's not 0, it's significant, and that if it's in between two numbers that are significant, it is. But this is the one to worry about. Okay, it's going to be 0, and it has to meet the following two special criteria. First, it's at the end of a number. And what else? Number. And secondly, it has to be to the right of the decimal point. That's what it is. If, in order for a 0 to be significant, it has to be at the end of a number to the right of a decimal point. So if you had 0.123, 1, 2, and 3 are going to be significant because those digits are not 0. This 0 here is not significant because, first off, it's not at the end of the number. Secondly, it's to the left of the decimal point. It's not to the right of the decimal point. And when you get back to measuring, think about this. The precision of the measuring instrument determines how many significant figures there are. Precision of instrument determines the number of significant digits. In other words, the smaller a measure that you're able to do because of how precise your instrument is, the more significant digits you're going to have. And I know this sounds like Greek right now, but you're building a vocabulary, you're learning some base words, some basic definitions that you'll need for chemistry. I'm going to stop this now because I don't know how much time I have left. Next thing that I'm going to talk about is scientific notation. Scientific notation is really cool. If you've never had it before, it's a sort of strange looking animal, but once you see how it works, it's really a really cool tool and something that will make your work a lot easier. So, until I see you for significant digits.